Algebra 1 students, welcome to your 6.1 notes, Solving Systems of Equations by Graphing. Through this chapter, we'll look at different ways to solve systems. And as you can see, the first of those options is the graph. Now, first of all, what is a system of equations? Well, it's two or more linear equations that use the same variables. The solution of a system is the ordered pair, or perhaps more than one ordered pair, that makes all of the equations in the system true. Now, when we're talking about two lines, what that would look like would be the place where the two lines intersect. You can read through the examples that you see here of when it might be used for tracking vehicles, uh, phone plans, which cell provider should you use, and then maybe something in biology like comparing the heights or weights of plants or animals. And we'll look at some different types of examples today and how we do this. All right. Suppose a puppy weighs 5 pounds at birth and grows at a rate of 0.25 pounds per month over the first several months of its life. A second puppy weighs 4 pounds at birth and grows at a rate of half a pound per month. After how many months will the puppies weigh the same amount? First things first, let's write the equation. Now, when we write equations, we need to make sure we understand what our variables stand for. So I'm going to do this. I'm going to say that X represents the age in months of the puppy. That's the thing that's changing, our independent variable, where Y would be the weight. So the puppy's weight is going to be determined by its age. Okay, so for the first puppy, the starting weight is 5 pounds. So this is puppy number 1. We know that the weight is equal to 5 plus, and then it grows at a rate of 0.25 pounds per month. The second puppy starts at a weight, it's a little bit smaller, 4, but it grows faster, half a pound per month. Okay, step 2 says to find the slope and y-intercept. Really what this is about is we're trying to graph, so we need to know how to graph those lines. So for the first one, our slope would be 0.25. Now keep in mind, 0.25 is 1/4. You're more used to seeing your slope written that way. Your y-intercept is 5. The order of these two equations is not exactly the same as our slope-intercept as we've switched things around, but it's still the same idea. On the second one, the slope is 0.5, which for our purposes finding slope, we'd want to consider that to be 1/2. And then the b value, the y-intercept, is 4. Okay, let's go ahead and graph these two lines. Again, the first one has a y-intercept of 5, so what I'm going to do is count up 5 spaces, mark the point, and the slope of this line is 1/4, so I'll go up 1 and write 4. I'm going to go ahead and do that a couple of times. Now here's something to think about it. 1, 2, 3, 4. This situation, we're talking about a puppy, and the x value represents age. So the question would be, does it make sense to go outside of the first quadrant? In other words, can the puppy be -4 months old like this point here? And of course the answer is no, you can't have a puppy that's -4 months old, so we don't really have to worry too much about any graphing outside of the first quadrant. All right. Let's graph the other line. The equation there was 0.5x plus 4. 1, 2, 3, 4. And the slope, as we said, is 1/2. So I'm going up 1 and right 2. And we found ourselves a nice intersection. Again, we can keep things in the first quadrant. There's really no reason to go outside of that. The key to this whole thing, though, is that we found this point right here. And that point is 1, 2, 3, 4, and up 6. So 4 and 6. The solution is the point where the two lines intersect. That's the point 4, 6. Now we have to put some meaning on this. If you think back to how we defined x and y, x was the age, y was the weight. So it says after how many months will the puppies be the same weight? 4 months. This question doesn't ask it, but after 4 months they would weigh 6 pounds each. All right, let's take a look at how we classify systems. We'll do some more graphing and solving momentarily. You can see the three scenarios here. The one on the far left is what we typically run into, where we have two lines that intersect each other. We would know if that happens that the lines have exactly one point of intersection. Therefore, the system would have exactly one solution. And we have a couple of words we use to describe this. Consistent, which means that that there is a solution, and then independent essentially means there's just one solution. Now our second example, you can only see one line there, but it's actually two. They just happen to be at the exact same spot. So in that scenario, the two lines intersect an infinite number of times. Each line is the same as the other. And so we call those consistent because there is a solution. However, that solution is every point on the line, so we call them dependent. They're dependent upon each other. The final scenario we run into is when we have parallel lines, as you can see here. There's no solution to a system like this because the lines never will intersect. So we would say that the system is inconsistent. All right, let's take a look at a different way to approach the same thoughts as the previous slide. It's a little flow chart for us. If you look at the slope, if they're different, then the lines have to intersect. Therefore, they'd be consistent and, of course, independent as well. Now, when the slopes are the same, you have to take a look at the y-intercept. Are they different? Then you have parallel lines, no solution, inconsistent system. If you have the same y-intercept and the same slope, then you're talking about two lines that are exactly the same as each other. So we say there are an infinite number of solutions, and the terminology is that they are consistent and dependent. For the last three problems, we're going to get some more practice with graphing to solve systems. So what I want to do on this, we have two equations. Neither of them are in slope-intercept form, so we want to go ahead and work that direction. So I'm going to add 4x to each side, multiply everything by -1. This answers a couple of questions. One, it gives me my y-intercept of +1. Also, it tells me that my slope is -4. Now, I like to go ahead and mark several spots when I'm drawing a line and finding a slope. The reality is, if I just mark the intercept plus one more point, I actually have enough to work with. But again, if we do more points than that, it might help us to improve our accuracy for our graph just a little bit, help us to find if we somehow made error somewhere along the way. Let's take a look then at the second equation, y minus 2x equals -5. I'm going to add 2x to each side. And let's take a look at this. The slope is 2. The y-intercept is where I want to start, though, at -5. And then we can apply that slope. Now, what I've noticed is right away, I found the point I was looking for, the point where the two lines intersect. It's this point right here at 1, -3. So we would write our solution probably as an ordered pair like this, 1, -3. You do have the option of writing x equals 1 and y equals -3. Again, my preference is the ordered pair, but there's nothing wrong with writing what x and y equal individually. Let's take a look at our next example. You can see the first is already laid out for us nicely. Y equals 2x minus 1. Let's graph that. There's my y-intercept of -1. The slope is 2, so I'm going to go up 2 and write 1. I might go down 2 and left 1 just to extend that the view of that line just a little bit. Again, at home, I would use a straight edge, whether it's a ruler or perhaps you have a protractor, or maybe even just using the edge of your book is fine, but do something so that you can get these lines reasonably straight. Now, to solve the second equation for y, we need to divide everything by 3, so y equals 2x minus 5/3. That's 1 2/3. And that's a little tricky for us when these two lines are so close together, but we can work with it. So we'll go with it. And the slope here is again 2, 1, 2, and 1. Now, if you're really thinking about this, what you might already have noticed before I even started sketching or attempting to sketch this line was that the two equations had the exact same slope but different y-intercepts. Whenever we run into that situation, we know we have parallel lines, which means there is no solution. It also asks us it says how many solutions, and then it says to classify the system. Well, these are inconsistent. In other words, the two lines don't intersect. Okay, so we'll look at our last example now. Again, we'll start by changing things into slope-intercept form. So we'll have y equals x plus 5, which means our y-intercept, 1, 2, 3, 4, 5, and our slope is 1. So we go up 1 and right 1, or of course you could go down 1 and left 1. And we can go ahead and connect. And there's our line, something like that. The second equation says 3y equals 3x plus 15. I'm going to divide everything by 3 here. Interesting. We've actually already graphed this line. It's right there. Now, the question says, tell whether the system has one solution, infinitely many, or none. So we would say this has infinite solutions. And we'd also need to classify this. This is a consistent system. In other words, we have at least one solution. But because it's exactly the same, we would say that it's dependent. I hope these notes help you. And when you come to class on Monday, we'll be ready to work. Have a great weekend.